Welcome to the fastest way to learn data structures and algorithms. Today, we're tackling a legendary hard-level challenge, LeetCode 212, Word Search 2. This is the ultimate test of grid traversal and prefix trees. If you can master this, you can handle almost any backtracking problem in a technical interview. Here is the setup. We are given an M by N board of characters and a list of words. Our goal is to find all the words from our list that exist on the board. A word can be formed by characters from sequentially adjacent cells, moving horizontally or vertically. But remember, we cannot reuse the same cell twice for a single word. Think of this as a dictionary scavenger hunt. You have a list of hidden items to find in a messy room. The brute force way is to look for the first item, then the second, then the third. That is exhausting. Instead, you carry a smart catalog, a tree. As you walk through the room, you check every step against your catalog. If you see a sequence that starts a word, you keep going. If you find a full word, you cross it off your catalog so you never waste time looking for it again. That is the power of tree-based pruning. To solve this efficiently, we use two powerful tools, a tree and backtracking DFS. First, we insert all our target words into a tree. This allows us to check for prefixes in constant time. Next, we start a depth-first search from every single cell on the board. As we move, we traverse our tree simultaneously. If the characters on our path don't match any prefix in the tree, we stop immediately. This pruning is what makes our solution lightning fast. When we hit a word marker in the tree, we add that word to our results and remove it from the tree to avoid duplicates. Look at the grid on your screen. We have a board with letters like O, A, N, and our word list includes OADH and PA. We start at the top left cell, row 0, column 0. The letter is O. We check our tree. Does any word start with O? Yes. OATH. We move to the neighbor, row 0, column 1. It is A. Does our tree have OA? Yes. We continue to T, and then H. We found a match. We add OATH to our results set and immediately mark it as found in our tree. Now, imagine we start at row 1, column 0. The letter is E. Our tree says no words start with E, so we stop instantly. We just saved ourselves from searching thousands of useless paths. In our Python implementation, we first define a simple tree node. In our main function, we build the tree by inserting every word from our list. Then, we define a recursive DFS function that takes the current cell coordinates and the current tree node. Inside DFS, we check our base cases. If the current character isn't in the tree node, we return. We mark the cell as visited using a temporary character to avoid reusing it. Then, we explore all four directions, up, down, left, and right. After the recursion, we backtrack by restoring the cell's original character. Finally, we trigger this DFS for every cell on the board. For time complexity, in the worst case, we explore every path for every cell. With pruning, it is significantly faster, but the upper bound is O of M times N, times 4 to the power of the maximum word length. For space complexity, we store our words in a tree, so it is O of total characters in the word list. And that is Word Search 2 mastered. By combining tries with DFS, you turned a massive search space into an elegant, efficient solution. If this helped you, don't forget to like, subscribe, and share with your fellow engineers. I will see you in the next premium guide.